So welcome to Cardiff University, who are here to tell us about the latest visual computing and machine learning research. And I have the great pleasure to introduce Professor David Marshall to do the first presentation. Dave, over to you.
Okay, so hi there. I'm Professor David Marshall. I've got Professor Yukun and Paul Rosen, two esteemed colleagues who will talk a bit about their research in due course. So before I start, a little bit about the Visual Computing Research Group. We're 12 strong at the moment and currently expanding. And there's a few nice photographs there which will be more relevant when Paul Rosen takes over in due course. So what is visual computing and what do we talk about? Well, we are the largest visual computing research group in the UK. And what does visual computing embrace? Well, it's 3D data processing. You have to think of meshes, but also other 3D data like point clouds and even depth maps. We do quite a lot of work in computer vision. That's our bread and butter. That links into work with video processing. There's a bit of computer graphics, and we also do a bit of audio multimedia work as well, embracing computer music as well. We do enjoy strong links internally inside the university and also externally. We have had strong medical-facing links. We work closely with our School of Engineering. As you will see with some of my talk in a few minutes, psychology. We also work with optometry and the sciences a bit. We do enjoy strong industrial links. Obviously, we got one with Orbital, and we've got strong links with Shared Space, Airbus, Retrieval, and many others. And also international universities as well. What I'm going to do is highlight, pick up some work. I can't cover all the work that the group does, and between the three of us, we'll highlight some of the key areas. Probably our main area is sort of 3D data processing. That's describing 3D shape, the solids, the surfaces, and how we might use it. One classic one we've been doing for quite a while is reverse engineering. That's actually trying to reverse engineer proper CAD models from underlying 3D data. We also do quite a bit of 3D data over time. We've got a scanner, and we've done some facial dynamics with that. As you'll see with Paul Rosen, we've done some analysis of old scrolls. We do 3D shape retrieval, geometry processing. Outside of 3D, some of the work which I've been doing and with Paul, and that is video surveillance. I'll mention a little bit about that shortly. Also 3D, we've been looking at in medical with our psychology brain imaging center. We're looking at how the brain, the 3D model of the brain will operate when you move your head around. And one theme I want to bring out is human-inspired psychology. To do that, okay. So I was asked to talk about some emerging areas of computer vision. So these days, machine learning and computer vision are quite ubiquitous. Deep learning has taken over a lot of the computing world, and we are no different. So deep learning is almost everywhere to do that. It's not to say it's completely solving all the problems. And one thing which is emerging now is that machine learning, especially deep learning, but other aspects as well, do tend to be a bit black boxy. We don't understand how they work inside. So now an emerging area is explainable AI, which we're looking at, as indeed many others are doing it. I think another area which is humans have evolved over many years to operate quite well, and sort of the cameras and computers serve humans more than anything else. So trying to sort of model and see how humans work and model how the human brain works is another area of growth in psychology research. And AI and machine learning. Okay, so there. Okay, so I'm going to briefly highlight a few topics I've been working on. The first one is spatial dynamics. This is one which I've been working for many years with, and recently enjoyed a good KTP with Orbital. So there's an example of somebody talking. We record their video, we record the audio, we machine learn the coupling, the interactions between the audio and the video, and the idea is then that you can actually synthesize a new face. I'll show an example. Other things we've been doing is conversational expressions, where we've got two people talking. So we basically got the single model working both ways, and then we can work and machine learn the interactions between two people. So they start smiling, laughing, and eye contact and the like. plenty of applications, talking heads, biometrics, aging, perception, and the like there. So here's an example of you may be talking, this is not me talking.
Oh, my name is Joe.
So we've managed to synthesize a convincing face with a female voice. Okay. Another example, which is best shown by a short video, is detecting violence in videos. Whoops.
As police forces face squeezed budgets, the scientists at Cardiff University, who are behind the technology, think it could help target problems before they get out of control. Our Wales correspondent Hal Griffiths has more.
So what you'll see on this one is some guy jumps up, and as he does that, we get a massive dip in quite a few of these graphs.
This computer system could, it's claimed, be the next advance, programmed to recognise the sudden, unpredictable movements that lead to violent confrontations. It can watch and warn the police.
The camera's looking at how the patterns that occur in the video change over time, and what we find is that violent footage contains more chaotic patterns.
CCTV technology now covers every British city. Here in Cardiff, 100 cameras monitor the streets. So many, it's almost impossible for human eyes to pick up on everything that's happening.
It's a sign of the times. So if we can supplement this by modern technology, by introducing ideas that haven't been introduced before, it will be fantastic. It won't replace the police, but what it will do is provide an additional tool.
Backed by the Association of Chief Police Officers, the appeal to Britain's police forces is clear as they look to the future of tackling crime. Howell Griffith, BBC News, Cardiff.
Okay, so the final topic I briefly want to mention is an example of where we can bring in some deep learning, but also explain how it works. And also here we've been inspired by humans. So humans exhibit surprise and expectation. Okay. Surprised that when you see something which you don't expect, and expectation is obviously the opposite of that way you do it. So can we actually introduce some ideas to do that? So what we do is we can try and analyze, we train a CNN, and then we look at the activation, which is the parameters, if you like, of the network, and basically we can measure the activation of certain things. If you get a high score in certain areas, we can say they're surprised, and if you get a low score, we can say that they were expected, and then we can use that to explain things. So if you can suppress surprise, you might actually be able to improve the network, because if the network's seeing surprise, it may not be actually that well trained, or it's got some things there. So if you identify pixels and then retrain the network where you see surprise, we can actually improve the classification of the image. And in this example, with this data set, we have managed to improve 36 misclassified images. The other thing to do is we can do explanation. And one thing here is you can see that you've got some examples here. This lizard's quite interesting in that we misclassify the lizard on the pink towel because, surprise, surprise, there's a pink towel, and pink towels don't exist in many lizards' world. So what we can do is if we highlight that the pink towel is the problem, replace it, replace those pixels, we can then improve and correct examples that way. So there's some examples of that, and that's it.
So thank you to Professor David Marshall for his presentation. I'd now like to introduce Professor Yukun Lai, who again is going to talk about the latest research into computer vision and machine learning.
Yeah, thanks, Pete, for the introduction. I will follow, Dave mentioned, we're going to talk about a bit more about some of our recent research in visual computing. I'll focus more on the 3D shape processing side. Why, AI need to understand 3D? Well, our living world is 3D, and in order to, sense and understand, in order to actually respond effectively to the 3D environment, AI should really sense and understand the 3D. And this actually has many applications, from creative design, how to help designers create nice designs effectively, to computer animation, assistant robots, autonomous driving vehicles to understand the environment, smart manufacturing, and virtual reality and augmented reality. So I'm going to show you some of our recent work. So first step we start looking at is how do we capture the 3D environment. So what we do is we can show that if the reconstruction process can understand the environment by using machine learning, we can actually improve the 3D capture because we now can use the additional information, the semantic information, to help us reconstruct better quality 3D geometry. In addition, if we have a really large environment to capture, one way we propose is that we can actually have some robots rotating in certain place for in-place capturing in these some selected locations to get some panoramas, which then can be fused to create a really large 3D environment in high quality. In addition to just capture the geometry, sometimes we do need to know the semantics as well. So we show examples where we use contextual relationships learned from some virtual things to help us build a semantic representation of the indoor environment that includes not only the geometry, but also the object type and their relative position as well. So that can be very useful if you later on want to improve your interior design by introducing suggested furniture, for example. Alternatively, if we have some interior design, we can augment that by introducing further decorations of small objects. Now, this we propose an active learning-based approach where people can only need to specify a small number of constraints, and the system can derive a suitable decoration more efficiently rather than tediously placing individual objects. In order to design some new shapes, it's often very tedious. So therefore, it's very important to try to reuse any design we already have. So from that perspective, we work on shape retrieval, which basically means that we can use some queries to retrieve relevant shapes. Now, these can be shapes which have some similarity to the query, but also sometimes we also look into cases where shapes can deform. So like the example, like human bodies, they can deform, and how we can effectively retrieve shapes even with large non-rigid deformation. Another side of it is we have a large collection of shapes. We can try to, if in order to find the relevant shapes, we want to provide an environment where people can explore that with sketches, with indications of their preference, so that we can actually gradually refine the retrieved shapes, and we can find the shapes they're interested in. This applies to global specification, but also local specification, saying this part of shape is of interest, and then we can find shapes with that particular similar shapes highlighted. For computer animation, it's often the cases that you can, if you have some starting shape and the ending shape, we want to create an animation sequence. This can usually be a very tedious process. However, thanks to this machine learning technique we developed, we can actually generate nice animation just by specifying the first shape and the last shape, and it learns the behavior of what a cat should behave, and then turns into an animation automatically from this lion to the cat. Now, once we have some animation sequence already, and if you want to apply to some similar objects, but they are a bit different, for example, in this case, if we have a human animation sequence, and we have a robot now, but how we can reuse that, we develop some method which can automatically transfer the definition of the first sequence to the second one. It's through a learning-based approach. We can identify how we can actually transfer the information of that definition from the existing one to the new shape. Now, looking at if some shapes, the new shape may have a different geometry. So, for example, the elephant has a trunk, but that doesn't exist in the horse. That can be automatically handled as well. Now, with some small alignment examples, we can even use like face animation to drive some sort of human body changes based on that specified mapping. For the existing shape you can retrieve, but the retrieved shape may not be the one that we want. So we can actually edit that shape. Now, traditionally, editing shapes means that you may need to do very tedious modification. Now, with these machine learning-based technique we develop, we can actually specify a small number of handle points. And because the algorithm knows how the object should deform, you only need to drag these small number of handles, these green dots, and the red one is the one being dragged. And it knows that how the leg should bend, and so on. So therefore, you can actually create nice results with a very small and intuitive interaction. So results are actually based on real-time screen recording. So in order to make the shape design process more efficient, we also consider a learning-based technique to generate 3D shapes. Now we're looking into shapes this kind of man-made objects which have rather complicated structure and also fine geometry details. So we use learning-based model to build to construct these kind of to generate these kind of shapes. This also allows us to interpolate shapes based on both geometry and structure. So these two given shapes, and if you interpolate both based on geometry and structure, we can generate all these new shapes automatically. We particularly interested in looking at how we can represent shapes with fine details and correct connectivity, and which is difficult with the existing methods. And in order to help designers, we can automatically generate lots of design shapes automatically for inspiration, or to help them as a starting point to make further editing and improvements. Now, shapes that do not just have the geometry, it's also that the texture is also very important. So we also developed learning-based techniques to try to model not only the geometry but also the texture. This allows we to generate these kind of interpolate the geometry and texture together. And if you have a 3D shape already, we can also suggest suitable textures which all look plausible. And we can also obviously generate random shapes with texture, a suitable texture attached, so that people can use that as starting point for adaptation to their needs. Now, not just about generation, obviously, as for the application we mentioned, it's also important to understand what's there in the 3D environment. So we're looking to ways to detect objects in the environment, so that, for example, an assistant robot can respond accordingly to pick up objects, for instance. And we also look at how we can, given the environment, how we can get a detailed separation of objects into things into objects, and segment object into different parts, and identify any symmetry from the object. For example, when you do the shape editing, knowing the symmetry means that we can edit one side, and we know the other side should be changed accordingly. Yeah, that's all for me.
Thanks, Yukun. Fascinating presentation. I'd now like to introduce Professor Paul Rosen from Cardiff University.
Okay, thank you, Peter. So I'm Paul Rosin, and I'm going to tell you about a couple of the projects we've been working on in the computer vision side in the group at Cardiff University. And so the first one is a project that we had on the virtual unrolling of scrolls, and we had a bit of publicity on this on the BBC One show. So I'm going to start off with giving you a short clip from the BBC One show.
A scroll, it's so ancient, its contents have remained a mystery.
Ancient scrolls are often so delicate and damaged that if you try and unroll them, they just fall apart in your hands and the information contained in them be lost forever. But a new innovation means that it may soon be possible to read the pages of history without ever opening them.
So this was the scroll that we were looking at for that program, and it's an old 15th century scroll which had some water damage. And the consequence of that was that although you can see it's partially unrolled there, it wouldn't unroll any further because it had become sticky and got jammed together. So any further unrolling would have actually damaged that scroll. So what we wanted to do was to be able to virtually look at the contents on the inside of that scroll. And we had an EPSRC project in collaboration with Queen Mary University, and the physicists there had built this X-ray machine, which is a microtomography machine, so it gives high resolution X-ray photographs. So back to the BBC One show.
The machine scans very fine slices of the scroll and then builds them up into a digital model made up from 11 billion 3D pixels. The scanned scroll is still rolled up, but Dr. Paul Rosin from the University of Cardiff has worked out an ingenious way to unwrap it digitally. So, Paul, what is this image here and what do you do with it?
So we get literally 10,000 X-ray cross-sections, which are showing a cross-section through the scroll as we go along the length of the scroll. And they have this bright outline, which is the parchment, and then the very bright points correspond to ink.
Right, so you've got a sort of a slice through the roll.
Yes.
And these little bright splotches, that's actually the ink.
That's right. So in all these cross sections, we have to extract out the parchment, we have to do the unrolling, we have to take all the intensities and then stick them all together to form the resulting image.
It's taken months to carefully line up thousands of these tiny slices. Today, Paul is going to show archivist Gary the result. If it's readable, it will be a world first. Okay, Paul, let's have a look. It's been 600 years since this has been read.
So this is what we could see before.
Yes.
And now we've uncovered all this.
Wow!
So as you see, it was quite dramatic there. But this slide here shows that really we had cracked it to at least a good degree. So on the left, you can see an image, an optical photograph of part of the scroll that was visible. And on the right-hand side there, you can see the sort of equivalent version that we have recovered from the X-ray scan. So we were able to do that not just for the visible parts, of course, but also for the hidden rolled up parts. So that's the first project I wanted to tell you about. I'm going to move on to something a little bit different now. And this is some work that I've been doing for quite a while now on non-photorealistic rendering. And so the idea there is that you have an image like the one here on the left-hand side, and you want to restylize it, as it were, to create different versions, such as the ones shown on the right-hand side. And you want to create these more artistic or more interesting versions of that image. Now, that's a sort of interesting topic, which is somewhere in between computer vision and computer graphics. And it saw a fair bit of work maybe 10 or so years ago, and then became maybe slightly less attractive. But interestingly enough, in the last few years, with the advent of deep learning, it's come back again under a slightly different guise. So now, instead of calling it non-photorealistic rendering, we call it neural style transfer. And there's been a huge amount of activity and a buzz with many, many people around the world working on this topic of neural style transfer. Now, you've probably heard about deep learning, and there's an awful lot of hype on deep learning, and people think maybe that it can do anything and everything, but actually it still has some quite severe limitations when you're trying to do some really specific sorts of tasks. And so in this case here, we have a target image, and what we'd like to do is we'd like to stylize it, or re-render it if you like, to make it look something like this one here in the middle, which is an artist's drawing. So we'd like to generate some sort of line drawings of these photographs of faces. Now, that's very challenging because, of course, faces are very special in human perception, and any errors that we have in synthesizing a human face will really be unacceptable. You know, if you ended up with a missing eye or an extra mouth or whatever, it just wouldn't look appropriate. And if we just throw some sort of standard deep learning approach, you can see here the results are really absolutely terrible. But even using more contemporary, more state-of-the-art techniques as the ones over here, you can see that they still have various artifacts. There are lines that are missing, there are sort of weird blotches in the image and so on. So we've spent a lot of time in the last few years developing a series of techniques that use deep learning to try to generate these demanding line drawing style portraits. And so you can see down here, this is our first result. And then subsequently, we did another version here where you can see we've improved that, and we've got something that looks really very similar in terms of style and quality to that artist's drawing. Now, we're still working on this topic, and this is actually some of our more recent work, where what we now have is, well, partly there was a technical change in the way that we do the training to make it more practical for us to train on large amounts of data. But another modification here is that you can see that we have a model now, this deep learning model, that will generate line drawings with multiple styles within the same model. So we can now generate 3 or actually any number of intermediate styles of line drawing, such as the one shown here. And these were actually derived from training from different examples from different artists to give us these different line drawing styles. And there are many potential applications that we could imagine for this sort of neural style transfer. There's generating graphic design, creating things for web pages and avatars and so on. But I'll just show you here a rather different sort of example to show you how even sometimes it can be a little bit unexpected on how you actually use these sorts of things. So this was a different project, which was to create 3D bas reliefs from photographs. The idea is that you start off with a photograph like the one on the left column here, and then you generate a 3D bas relief, which is essentially something like a coin, the sort of three-dimensional structure that you could have on a coin, which could be useful for, let's say, some sort of bespoke manufacturing. And what we found was if we did some stylization of the image, as shown in this second column here, what it does is really it just cleans up the image, makes it more attractive, and it made the resulting bas relief also more attractive. You can see it's looking rather good there. So I'm just going to finish off with this slide here. I'm not going to go through all the individual projects shown there, but it's just to give you an indication that in the group here, we actually are working on many different computer vision projects, some of them more research related, some of them more application related. And certainly if you're interested, we can discuss some of these and other things that you might be interested in too. Thank you.
So thank you for 3 brilliant presentations. It's certainly given me some food for thought in terms of potential collaborations between Orbital and Cardiff in the future, and that's fantastic. So I'll head straight into some questions for Paul in terms of your presentation. And the first question is, what do you think the limitations are for your methods for virtual unrolling of scrolls?
Well, we have at least a couple of technical limitations. So the first thing is that the X-ray scanner has a limitation on size. And the physicists used to tell me that really the things had to be able to fit inside a Pringles can or case or whatever you like. So anything larger just wouldn't fit inside. And there's a sort of physics limitation that if they tried to build the machine bigger, then power has to increase 8-fold, which would mean that it would fry the content. So that's not really acceptable. There's another limitation, which is not also easy to overcome, which is that we really rely, to find the ink, we rely on some contrast inside the X-ray scan. And so, unfortunately, what that means is that certain inks, which are made of a different sort of substance, just don't appear. They don't show up in the X-ray. So therefore, no matter how much fancy unrolling we do, we can't see anything. So these are the 2 main limitations to be able to sort of apply to anything and everything.
To me, it just offers up so many opportunities to unraveling lots of historical mysteries, and I guess you're almost chomping at the bit to try and explore the technology and take it further, and to try and unravel some of these questions. Has anything of historical interest been discovered so far in terms of your exploration with this technology?
Well, not quite as yet. Nothing earth-shattering. We've had a few hopeful leads with the 15th century scroll that I showed you in that presentation. We did manage to recover quite a lot of text, not all of it, but we got a good 20–30% of the scroll, which could be read by an archivist. It's written in some sort of, mostly actually Latin, because that was a legal document from a manor house. And they managed to find little bits and bobs relating to fishing rights and other legal stuff. So it was interesting. Now, we did have some other scrolls that we got access to that we're really quite excited about, but unfortunately they came to nothing. So one of them was from an Arctic expedition, and I've forgotten the name of the explorer. It wasn't Sir Robert Scott, but it was a camp that had been left there when he, I think, died, and they found many years later some documents which again were rolled up and couldn't be unrolled easily. And so we went through the process, we put it in the scanner, we're really looking to see whether it was some sort of last will and testament, but unfortunately there was no X-ray contrast, so we couldn't see anything inside the X-ray.
Fantastic, fascinating. And in terms of the scrolls and potentially other opportunities outside of analysing scrolls, what do you think the applications are for the technology, how it's going to move forward and develop over time?
Well, you can definitely imagine putting other things in there that aren't, strictly speaking, these parchment scrolls. And actually, we did do a bit of work on another project, which was on films. So if you think about it, a film, like a movie film, is a little bit like a scroll. It's like a spiral rolled up. It's made of a different substance. The ink is also not ink, but nonetheless, it's still got the same sort of characteristics. And we were given a little bit of data from actually an old episode of Markham and Wise, dating back to the 60s, and they had this recording that they had made of a Markham and Wise show that had been lost, as it were, for the last 40–50 years, and was rediscovered in some sort of storage shed in Nigeria, and it was very quickly degrading because, you know, acetate doesn't last forever. And so what they did was they cut it up and stuck little bits of it inside the X-ray scanner. And we had a look at one of these bits to see whether we could recover the contents. And although we only had a small part, actually we were able to recover some stills from this video. The trouble is we weren't given access to the full data set. I guess it's, well, somebody else owns it and somebody else wants to get the glory, if you like. But the plan was that they were going to try to do a reconstruction from that using maybe other techniques and even see if they could recover not just the video, but even the sound as well. So there are definitely many different applications, whether it's scrolls of parchment or scrolls of other stuff that could be quite workable in the same framework.
Excellent. It's going to be really fascinating to see where the technology develops and which pathways it goes down in the future. Thanks, Paul.
Thank you.
You can, in relation to your presentation, can you give some examples of how this technology can be used in practical applications?
Well, I mean, I probably showed quite a few variety of examples, but one thing we can see is that, for example, if we can capture our room and represent that into in the 3D representation, then that can be used for instance, where for furniture company they can say, okay, we can give you a recommendation what furniture should be suitable in your current setting of your room. Other possibility include, it can be any interior decorations or anything that give you the impression. You can actually see what it will look like when if you buy this product, you can see what it looks like in your house. Now you can also put that into a VR settings. You can feel more intuitively. You can walk around and see what your new house will look like.
Brilliant. And what do you think about the future of such technology? Is it going to replace designers anytime soon?
Well, I'm not, certainly that's not a researcher's intention. I don't think, and also I don't think that will happen, at least in the reasonable future. I think the reason is these technologies are designed to help designers to make their, basically to focus on creative work. So there are lots of tedious tasks. We know that designers used to have spent lots of time, building intermediate frames just to generate a short animation, or spending lots of time just to modify a shape to suit their needs. But what we want to do is provide designers with powerful tools based on machine learning so that they can focus on anything that's creative. I think that creative side can't really be replaced any soon by pure AI, and also it all depends on how people perceive. We want to appreciate art, and these arts can't just purely be generated by computers, at least for the time being, right?
So you see it as a way of augmenting creativity.
Yeah, basically that's what we aim to do. Yeah.
Fantastic.
Thank you.
That's brilliant. So Dave, so just wanting to talk more sort of generally about computer vision research and machine learning. What is the future of visual computing from your perspective, do you think?
A tough question, and I think if you look at the last 5 or 10 years, it's been revolutionized by it. I think a few things. I think linking into what you can say, we now have some very powerful techniques, and but they're sort of hard for us to understand some of the deep learning. Let alone for the users, like with Yukun, the designers, and whatever there. So maybe if you can get explainable AI to then help users and explain it and make it more usable, I think would be one thing. The other one is, of course, everyone's got a camera. We got brilliant cameras in all sorts of devices these days. So the amount of visual data available is astronomical these days. So there's loads of applications we can do that, and it's just becoming cheaper. So to do that. So, but I think making it more usable would be one thing.
So broadening out its capabilities.
Yeah, broadening out capabilities.
Yes. Technology.
Bring it to the masses.
Yeah. And how will humans inspire developments, do you think, in this context?
Okay, well, I mean, the human brain is incredible. I mean, we don't fully understand how it works, but obviously we know it's it's there, and we've evolved to do it. So I think that there are plenty of ideas there, and broadly the neural architectures that we've been using for a long time in machine learning have some inspiration by it, but they aren't really modeling the brain at all to do that. And I think what you're seeing these days in deep learning is we have some very clever routines which can be trained and tuned to work well on a very restricted domain, but then they don't generalize too well. And generalization is a problem, because you either need an unwieldy network, or you or you need a huge amount of data to do it. So be able to train smaller networks more compactly and put it together in clever ways, interchangeable, sharing information with certain pathways to do it. And there's inspiration in other brain networks work there really. So I can see these things there, even though we aren't directly modeling every synapse in the brain directly.
And I mean, it already feels like some of these technologies are kind of behind the scenes, already infiltrating our day-to-day lives. But what do you feel that the industrial impact for these technologies will be in the near future?
Okay, well, I think visual computing in general, the transfer of research into industry is pretty fast and probably as fast-paced as any to do it. And I think the drivers are the affordability of sensors, cameras these days is so great, and the availability of good computing power, which is now relatively cheap as well to do that. So the transfer to it is there. So and it does infiltrate life already. You got monitors in factories have been going for years, and that becomes more intelligent. Industrial robotics has been using this a lot to control things, and that there, and we got all the cultural aspects and other things there. So I think it's just going to increase almost exponentially. I think into all areas.
Yeah, I think I agree, Dave, and I think I guess that leads into the next question, which is if it is going to expand in terms of its use, what do we have to guard against and think about in terms of ethical issues in relation to its use?
Okay, well, I think of the talks we did today, the obvious most relevant one is being able to generate very realistic looking avatars or even human motion with Yukun stuff to do that. So clearly there's the deep fake, which is quite a hot sort of press topic these days, and the like there. And we are probably getting to the stage where certainly I think for small clips of video, it's very difficult to really detect if that's been synthetically generated or not. There are issues there for legal aspects. Is this going to be usable in court? And we have done some work on detecting forged images and whatever. People forge images for all sorts of other unethical purposes as well. Even forging image, your face to actually log into a person's smart device or online. There's all things there to do it. There's the ones then obviously if it's a famous person, a politician or whatever, you can then put words in his mouth which are either more inflammatory than that person or even counter that, and it's difficult to do it. So I think there are a lot of issues there, and it is hard to detect it. I think on one side, and I know we've talked about this before, is that if you are generating material, then there's a whole area of putting in watermarks or some sort of way of protecting the data. So if you are putting your data out there as a model or as a sequence, there might be ways you can protect that video from doing it. But again, you could be recording my face now, talking now, and then you could probably take that and turn the words into something there. On the other side, obviously, we've seen plenty of good comedy programs, famous movies where this has been used very creatively. So it's a difficult thing there, but clearly the ethics of stealing people's identities and inflaming things is obviously quite prescient at this moment in time.
Brilliant. And I think my company, Orbital Global, was incredibly fortunate to secure a knowledge transfer partnership with Cardiff University and your department, and that was a program to develop some technology to engage patients in healthcare and use some of these computer vision technologies to create avatars and machine learning responsive interactive systems that can improve that process. But maybe you can talk a little bit about that KTP process, which is obviously backed and funded by Innovate UK. What was the technology that we developed together, and talk a little bit about the process for that development of that technology.
Okay, if I talk about the process first, you saw in one of my earlier slides the idea of a talking avatar to do that. So we're taking work which Paul and I had been developing for quite some time at Cardiff, and the KTP is a fantastic way to transfer technology. So we had this technology, you had a really interesting need, we managed to meet somehow and take it forward. And the idea was we could develop and evolve the talking head technology where in this case, we wanted to have a way that we could put words into GPs' mouths, if you like. And the nice thing about it is that if you can just put in new audio, either from speech to text to speech, sorry, or people can maybe just phone in or record at home. That's a lot cheaper than taking the video camera network into somebody's house to do that, and probably a little bit better than setting things up with a webcam or something to do that, so you can do it. And the KTP process is I think works really well, and certainly from a university point of view, if there are any academics out there, you should be looking at these things as a really good way to do it. But I think from a company point of view, it's a very cost-effective way to do it. Quite favourable funding from the KTP, certainly for SMEs, but even large companies can benefit from some things there. So it's a really good program for transfer of technology, and it's exciting for us at the university. We can get our research out into the wide world much quicker than a lot of other avenues to do that, and that's very important for the university, of course, and to get impact and the like there.
Absolutely, and from a business perspective, we were incredibly fortunate to tap into this cutting-edge research to solve this pressing problem in healthcare around patient education and interaction. So to work with Cardiff University in trying to produce a solution that could improve that situation was a fantastic opportunity to solve a problem, but also grow, commercialize, and scale up a new business at Orbital, which is now called VirtTuri, which is spinning out of Orbital, which is a great achievement for us. And of course, there are all the other benefits of working with a university in terms of that sort of tapping into that knowledge post KTP, publicizing it, and securing the intellectual property afterwards to protect the findings. I think all of those things were incredibly important from our perspective as a business. And as I say, we were incredibly privileged to work with you guys on that project and to secure a piece of technology that could potentially save lives and improve healthcare outcomes in the future. So I think just moving on from that, where do you think your research that you presented today, where does that offer commercial opportunities for business to collaborate with you now and in the future?
Okay, well, I think all of us chose our more business-facing research to show for this one, so to do that. But I think they are. I mean, the avatar stuff, obviously, with you, but there's media and lots of other avenues there. I think the other one is, turn and said, can you use these things to detect things like fakes? Is another area that we are looking to exploit. The video analysis surveillance. So we've had links with sports analysis as well as doing the violence in the streets. So there's plenty of things there. And the amount of video out there these days is so huge, and there's potential in all areas, from defence, military, security, to just monitoring pedestrians in shopping precincts and the like there, if they ever get back out to do that. So I think Paul's technologies there, obviously heritage stuff. There's plenty of work to be done there, and if you can find other techniques or other scrolls, but maybe there's potential. I mean, Paul mentioned the fact you can't sense these modalities there, so maybe there's research, maybe more physics and computer in there to actually develop better sensors which can sense the 3D things, and then we can apply our techniques to it. So maybe we can drive other technologies to help there, because as we talked there, the heritage side is huge there, and I think Yukun stuff speaks for itself as well. There's the you mentioned the furniture designers, stuff there. There's a lot of work there to do it. But I think a lot of the work which Paul mentioned briefly on the slide, and maybe I mentioned as things which you hadn't covered, still has a lot of commercial impact as well. I think we are fortunate in our discipline, as I said before, that there's a strong transfer of our research and the capabilities of our research into tech. Perhaps we're lucky to be in this exciting area. And with machine vision, machine learning, driving the vision, and AI as well, getting more powerful. I think it's only going to actually get more powerful and interesting times ahead, I think.
Yeah, I think from a business perspective, I only echo that this feels like one of the most exciting strands of machine learning and artificial intelligence work, and I think it seems like the possibilities for engaging with academia to develop these technologies seem significant and pretty infinite, really, in terms of where they could head off into. I think I'd just like to say I think it's been a real privilege to have you on today. I think to have what I would consider three world-leading experts in this field in visual computing, machine learning. I would also say that having done a knowledge transfer partnership with Cardiff University, it was an absolute joy over 2 years, huge benefits emanating from that. And I think, from our perspective, we're certainly looking for additional knowledge transfer partnership opportunities to work with Cardiff and any other businesses that are out there considering tapping into the latest research for visual computing, then Cardiff University really is the place to go. And I strongly recommend getting in touch with Dave, Paul, or Yukun to have a conversation about potential opportunities for collaboration. But I'd just like to say a huge thank you for your time today. I know it's very precious and you guys are very busy, so it's been a real privilege to have you on and to thank you once again. Thank you.
Thank you.
Thank you.